Hello, and welcome to a reintroduction of Richard Feynman. About Richard Feynman. He was born May 11, 1918 in New York, United States, and died 1988 in Los Angeles, California. His family includes but is not limited to 2 sisters, 1 brother, his wife Gwyneth Howard, his son Carl Feynman, and his daughter Michelle Louise Feynman. He studied at MIT for physics and got his doctorate at Princeton University, and he worked as an associate professor at Cornell and was professor of theoretical physics at Caltech. Notable achievements, discoveries, and theories of Feynman include receiving the Nobel Prize for his work in quantum electrodynamics, which includes the introduction of Feynman diagrams. He devised a quantum mechanical explanation for Lev D. Landau's theory of superfluidity, as well as a theory that accounted for most of the phenomena associated with the weak force. He also developed the theory of partons and the parton model while working at the Stanford Linear Accelerator with a group of researchers. An introduction to quantum electrodynamics. While large objects in the world around us can be described using the theory of relativity, it's not of much use when trying to describe things at a very small scale. At the level of atoms and subatomic particles, objects behave very differently, and quantum theory is an attempt to describe the behavior of matter and energy at this subatomic scale. When talking about the behavior of light, although most of us would say that light travels in a straight path, this has been observed to not be the case. Photons are very small and light, and consequently do not follow the general rules of relativity. As a result, photons that are shot out do not have to follow any particular set path or trajectory. It's actually impossible to model the trajectory of a photon. Instead, you get a photon detector and put it some distance away from the source of the photon, then calculate the probability that the photon will make it to the detector. Feynman diagrams show the position of photons at a certain time, and as it is the easiest formulation to understand, I will introduce QED through these diagrams. Richard Feynman, Shinichiro Tominaga, and Julian Schwinger were co-awarded the Nobel Prize for Physics in 1965 for their fundamental work in quantum electrodynamics. While Tominaga and Schwinger were more heavily focused on intense complex mathematical equations, Feynman made the whole process intuitive to use by representing each equation with visual diagrams. I won't get too deep into the equations to spare you all from a headache, so here is an extremely basic overview of QED. This equation is the general formula used to calculate the probability amplitude for a transition of a quantum system. This is the representation of the S matrix, this is Wick's expansion, and this is the QED interaction Lagrangian. Here's an example of a second-order process in QED. This will be your second-order perturbation term for the S matrix. Wick's expansion will show this, and the result is this Feynman diagram. I will Feynman diagrams in detail. When 2 electrons crash into each other, we usually use the electric field and considerations like conservation of energy to calculate this interaction. However, a form of photons make up the electric field, and so, when 2 electrons approach each other, they scatter by emitting and absorbing a photon. Using standard energy and momentum, the electrons recoil away from each other. This interaction is represented as so by the Feynman diagram. There are other diagrams as well. Sometimes 2 photons will be exchanged, however we are unable to identify which photon corresponds to which electron. It is also possible that one of the electrons could exchange a photon with itself. This is called electron self-energy correction. Another case shows that a photon could temporarily turn into an electron and antimatter-electron pair. And lastly, these can combine to form any number of different cases which correspond to their respective equations. Feynman diagrams allow us to visualize all things that are possible, but it doesn't have to be so complicated. They all result to the same basic outcome: 2 electrons scatter. Each time a photon interacts with a charged particle, the chance that it happens becomes less and less likely. 1 extra photon drops the probability to 1%, and 2 photons drop it down to 1% of 1%, etc., etc., meaning that the more complicated Feynman diagrams are, the far less likely they are to happen. It is because of this that very precise calculations can be made by incorporating the other diagrams, as all diagrams correspond to an equation. This is only a very basic overview of quantum electrodynamics. However, it is undoubtedly the most accurate theory ever devised, agreeing to parts per trillion. It is sometimes referred to as the joule of physics. QED and Feynman diagrams have had a huge impact on today's society. From a physics perspective, QED was used to precisely model some quantum phenomena which previously had no classical analogs, such as the Lamb shift, the anomalous magnetic moment of the electron, and more. QED being able to predict the outcome of certain interactions, including the collision of electrons inside a particle accelerator, is used in the Large Hadron Collider to hopefully detect things like the Higgs boson, quarks, gluons, supersymmetry, and more. Feynman also had a series of lectures on QED, which were transcribed and published in 1963. The Feynman Lectures on Physics Volume 3 became a classic physics textbook written by Feynman. How Feynman's educational, family, and cultural background plays a role in his work. Well, Feynman's family and cultural background didn't really influence his work that much. His education was very important. Feynman got his Bachelor's of Science at the Massachusetts Institute of Technology in 1939. While studying at MIT, he proposed an original and enduring approach to calculating forces in molecules. He had a perfect score on the graduate school entrance exam to Princeton in physics, outstanding scores in mathematics. However, he did poorly on history and English. He was a research assistant at Princeton from 1940 to 1941 and got his PhD from Princeton in 1942. At Princeton, with his advisor John Archibald Wheeler, he developed an approach to quantum mechanics governed by the principle of least action. This approach replaced the wave-oriented electromagnetic picture developed by James Clerk Maxwell, with one based entirely on particle interactions mapped in space and time. Feynman's method calculated the probabilities of all the possible paths a particle could take in going from one point to another. During World War II, Feynman served as a staff member of the U.S. atomic bomb project at Princeton University from 1941 to 1942, and then again at the new secret laboratory Los Alamos, New Mexico, from 1943 to 1945. At Los Alamos, he was the youngest group leader in the theoretical division of the Manhattan Project. With the head, Hans Bethe, he devised the formula for predicting the energy yield of a nuclear explosive. He observed the first detonation of an atomic bomb on July 16, 1945. He was the professor of theoretical physics at Cornell University from 1945 to 1950 and was appointed professor of theoretical physics at the California Institute of Technology from 1950 to 1959. As well, Feynman holds the following awards: the Albert Einstein Award from Princeton, the Einstein Award from Albert Einstein Award College of Medicine, and the Lawrence Award. Ethical issues regarding Feynman's work on QED. There was one person who was not awarded the Nobel Prize but worked on QED, proving that Feynman, Tomonaga, and Schwinger's theories were one and the same. His name was Freeman Dyson. Dyson was the one who proposed the S-matrix theory, which unified the relativistic quantum field theory of Schwinger and Tomonaga with the space-time diagram theory of Richard P. Feynman. However, he deemed his work less important compared to the work of the other three, and since the Nobel Prize can only be co-awarded to 3 people, he gave up his place in the recognition. It should also be noticed that Tomonaga and Schwinger weren't as popular as Feynman. All the credit regarding QED is most commonly given to Feynman. You will almost always hear Feynman's work, Feynman's writings, while Tomonaga and Schwinger's work are often put off as a side note. Feynman's work, teaching, and contributions to QED theory reached near legendary status within the physics community. Although Tomonaga and Schwinger and Feynman were all working on the same project, It seemed almost as though Tominaga and Stringer became shadows of Feynman, as everyone started praising Feynman for his work in quantum electrodynamics. Now, that's not to say he was not intelligent. I wouldn't even be able to amount to 1/10 of his intelligence. Feynman was also not the most fortunate, although he was quite popular amongst the scientific community. Many Americans saw him for the first time when he was already ill and fighting against cancer. He conducted a dramatic demonstration at a televised hearing, confronting an evasive NASA witness by dunking a piece of rubber seal in a glass of iced water to show how predictable the failure of the booster rocket's rubber seal might have been on the freezing morning of Challenger's launch. Feynman was a really cool guy.